three. This is a three-lecture series. Well, I'll talk about my recent work on this derivation of the hard sphere Boltzmann equation. So this drawing work with Zaher Hani and Xiao, both from University of Michigan. Okay, so the plan is that today we're going to talk about the setup, the background, setup of the problem, and then maybe some rough ideas, like intuitions, how our proof works, and what is the main ingredients in it. And next two lectures, we'll be discussing kind of in more detail the ideas in the proof. So first, kind of time layering argument and kind of the cumulant expansions, and then the kind of the algorithm to deal with these combinatorial structures. Okay, so we start maybe with this the basic setup, the scope of the problem. So we are talking about derivation of Boltzmann, but before that, so we'll put in a more general, bigger picture of deriving these fluid equations. So the first question, derive the fluid equations from so-called first principles. Okay, so here fluid equation means, for example, Euler and Navier-Stokes and kind of related systems. So for example, in undergraduate physics or undergraduate mathematics, you will see kind of these kind of formal derivations of this Euler equation, for example, without viscosity, or Navier-Stokes with viscosity, where basically you start with you have a fluid, so and you put little piece of the fluid, and then you consider the forces that it experiences in each directions. Okay, and then you consider you use a Newton's second law to derive the equation of motion of this, and you get the equation of velocity. So this is not the kind of thing we are talking about, because this model basically preassumes that your fluid is described by continuous velocity field and continuous density field, and you kind of derive an equation based on that assumption. But really, we in the actual physics, we're thinking of fluids as made of actual molecules, like the fluid molecules. So in the case of gas, it's air molecules, and they kind of they have their own kind of microscopic motions, and they have their own microscopic interactions. And then our goal is to derive these macroscopic fluid equations from these interactions, kind of these microscopic objects. Okay, so basically we start from this system of particles. I try to get to the continuum fluid equations. Okay, so this was a major part of the so-called Hilbert 6 problem, where in the so historically this idea was first kind of raised by this work of Boltzmann. So we have Boltzmann 1870s, and before that, the earlier discussions of Maxwell. Okay, and these physical kind of considerations made Hilbert motivated Hilbert to raise his sixth problem, which was kind of major component of it is to establish, mathematically establish the kind of the passage from left hand side to right hand side. Okay, so since that time, there have been more than 100 years, and now this question is still kind of open as of now. And of course, people have a lot of important fundamental works concerning that. And basically, there has been a kind of strategy of doing this via the intermediate kind of object of the Kant equation, in which in this case is the Boltzmann equation. To have this basically we can view this as a two-step process that we start with the system of the particle system, which we'll describe on the microscopic level, and we go through this intermediate so-called mesoscopic level, and we pass to the macroscopic fluid equations. Of course, there are other strategies, but this one has been kind of a pretty successful strategy as of this time. So we'll see. And this is the Hilbert 6 problem. Okay. And then so there is we first talk about the kind of the first limit, which is the thing we'll be focusing on in this series of lectures, and then we'll briefly discuss this second limit, which is kind of better understood at this time, and then we'll conclude with some of the ideas, in our recent work and in our proof. Okay, so let's start with this. So the first limit is basically the so-called kinetic limit, where basically the kind of degree of freedom goes to infinity. So, okay, so let's see. So from the particle system to Boltzmann. Okay, so the idea is that we start with the system of particles. So consider a system of n particles. So n you can view it as a degree of freedom. So n will go to infinity in the limit. Okay, and we assume that these particles kind of are of a small size. So the particles have size epsilon. Epsilon goes 0 in the limit. And basically, these particles kind of they interact at scale epsilon. Okay. So the kind of interaction we are talking about in this lecture is the simplest kind of interaction, which is just a direct collision. But of course, in practice, you may have more complicated interactions given by potentials and so on. But in any case, essentially these interactions happen at scale epsilon. So think of this picture. You have finite, fixed finite volume kind of domain, and then you are going to have this size 1, let's say. Okay, and then you are having a lot of particles, okay, so kind of occurring, existing in this domain, and that can kind of going randomly, like okay, in random directions, and then maybe two of them can collide. Okay, they can interact, and when they do interact, okay, they are going out with two different velocities. Okay, so and then you think there are so many particles, the number of particles goes to infinity, and the size of the particle goes to 0. We'll see there is a particular scaling law involved in this problem. But in any case, you have all these kind of interacting system, and now we're going to derive from this interacting system the effective equation that describe the statistics of these objects. And then we're interested in the statistical description of the system. Okay, so let me explain why are we interested in the statistical picture. The reason is that we are thinking of all the particles as the same. They are not distinguishable. So really, we are not interested in the particular trajectory of any one particle or any two particles. Really, we're interested in the distribution of particles in the sense that if we have region in the space, then how many, what portion, how many portion of the particles is in this region. And for example, if we give a region in the velocity space, then what portion of the particles, will have their velocity in this region. Okay, so these are given by the density functions. Okay, so basically, what the question is, what portion particles belong to a general, let's say, to a given domain or in a given velocity domain. Okay, so asking these kind of questions, and the answer to these questions is given by this density function. So basically, for the simplest case, we have the one particle density, which is so we have the one particle let's say F equals F T Z equals F T X V. So here F is the density and T is the time, of course, and then Z is a so-called the phase space. So it's formed by this X, which is a position, and V, which is a velocity. And this function is really just the probability density of finding a particle at this position X and at this velocity V. Okay, so this density you can see that describes the distribution of these particles. And instead of one particle density, you can also talk about the two particle densities, or kind of the S particle densities. If we have F equals Fs, T Z1 Zs, F T X1 V1, XS Vs. Okay, so here T is the time. Again, Z is the Zj is the position and velocity of the particle J. So this object means the probability density of finding a particle, finding the first particle like at x1 1, finding a second particle at x2 v2, and finding the S particle at xs and vs. Okay, so basically, the statistics of our system is completely described by these S particle density functions, and this is the kind of the object we are interested in. Okay, so this is kind of the first limiting process. We start with the particle system with a particular interaction, so we'll see this in detail, and then we take this kinetic limit where the number of particle goes to infinity, the size of particle goes to 0, and then we want to analyze these one particle densities and maybe the S particle densities that describe the statistical behavior of the system, and we're expecting that these densities are going to satisfy the so-called kinetic equation, which in this case is Boltzmann equation. Okay, so then we expect the density, one particle density, is described by the Boltzmann equation. Okay, so of course we'll describe what is the Boltzmann equation and why do we expect to have that. We'll describe it in more detail when we talk about the precise description of the systems. So this is overview of the first limit. Okay, so once we have the first limit, we go from particle system to the Boltzmann equation, and then there is a second limit which is called hydrodynamic limit. And here, basically, there is a quantity basically corresponding to the collision rate in the particle system. So this quantity that goes to infinity. So there is a quantity so-called alpha. We'll see later on alpha equals n times epsilon d minus 1. So this goes to infinity. Okay, and from this Boltzmann equation, you are deriving in this hydrodynamic limit, you are deriving the fluid equations. So since this is not the main topic of this talk, I only describe the kind of very rough ideas, how to how this works. So this is the second hydrodynamic limit. So basically, the idea is we start with the Boltzmann equation. So we start. So we'll see the form of Boltzmann equation is like let's be the f equals some okay, so basically there is a alpha times QFF. So we'll see what the right hand side is, and this alpha is a parameter that will go to infinity as we'll see. Okay, so this is, so we start with the Boltzmann equation, and then we're considering this the so-called local Maxwellians. Basically, such functions are functions of form. There is basically there is a rho. Okay, so rho t sorry tx, and then we have dimension over 2, so e to the minus v minus u. Okay, so this ansatz basically means that if you're given t and x, okay, so the kind of the probability density of this probability density in terms of the velocity v is a Gaussian function in v. You see, this is a Gaussian function in v, which basically means that these particles kind of have their velocity distributed in a normal distribution. Okay, so and then of course this normal distribution is centered, at this particular u, which you can think of as the kind of overall kind of average velocity of at this position position x in space, and of course rho represents the density and t represents the kind of the temperature. Okay, and basically what you do is that you start with this ansatz, you try to plug this into the equation, into this Boltzmann equation, and then you can and you let alpha go to infinity, and then you are going to perform asymptotic expansion in the parameter 1 over alpha, which go to 0, and then by collecting the kind of the terms of each order, we're going to get performing kind of Taylor, okay, not necessarily Taylor, but kind of expansions in 1 over alpha, we get the fluid equations at each order. So basically here the the u here, u equals utx, it corresponds to the velocity field. Okay, so this is how you actually get this continuum velocity field by starting with Boltzmann equation and looking at the kind of the overall velocity, the center of the velocity distribution as a Gaussian distribution. And then the kind of rho equals rho Tx corresponds to density. And then Tx is related to the pressure term. Pressure. Okay, so I'm I'm not involving too much details because it's not our main topic, but just know that there has been a way of deriving the kind of these fluid equations starting from Boltzmann equation. And this has been done, for example, this work of Cavendish in 1980s, and then the work of Damasi, Esposito, and whom Lebowitz, 1989, work of Gauss and Saint Raymond, 2004, and then more recent work of Gallagher, Tristani, 2019. So there has been a lot of results in this direction, and the derivation from Boltzmann to fluid equation has been complete, in many of canonical cases. Okay, so this is a basic kind of a description of this two-step, strategy. You will first start from particle system. You go from go to the Boltzmann equation in the first limit, and then you go to these fluid equations in the second limit. So for the rest of this talk and for the rest of this lecture series, we're going to focus on this first part, where we go from the particle system to the Boltzmann equation. Okay, so let's discuss this in more detail. So the first thing I want to clarify is that so remember we're having these two parameters in the kinetic limit. So the number of degree of freedom goes to infinity, and then this epsilon parameter goes to 0. Okay, so there is a relation between these two parameters called the scaling law, and here so now we proceed with the discussion the kinetic. Okay. So first, this so n number of particles, and then epsilon is a size. Okay, so if you consider a single particle, we fix let's say one particle. Okay, so we fix one particle here. And then let's say this particle is moving at velocity 1. And then if we go through time 1, okay, then it is going to cover a domain in space. And this domain, which will have a kind of a size 1 in one direction, in the direction where this particle is moving, and then it will have size epsilon in all other directions because this particle itself has size epsilon. Okay, then the volume of the domain is epsilon to the d minus 1, where d is the dimension. Okay, and then if you think of the total number of particles is n, if you think these particles are kind of evenly distributed in the whole space, then the expected number of other particles that kind of come into this domain. So some other particle may come into this domain, and if this particle come into this domain, then they will collide. They will collide with a given particle. So this expected number of other particles, which is also equal to the expected number of collisions, is equal to n times epsilon d minus 1, and we're calling this parameter alpha. Okay, so this alpha is kind of where we may refer to it as the collision rate. Okay, or basically kind of think of 1 over alpha, which basically the length, the size of so-called mean free path, kind of the distance that the particle travels before it collides, before its first collision. Okay, so these are kind of equivalent descriptions. Okay, so in our limit, we're going to set this alpha to be a constant. So we set alpha equals constant. In other words, n equals epsilon to minus d minus 1. And this so-called Boltzmann graph scaling. Okay, so this was introduced by Grad first in 1940s, 50s. I think, so Grad, 40s, 50s, I think, who was the first one to realize that you actually can expect to derive the Boltzmann equation under this particular scaling law. So that's that you're expecting this Boltzmann equation in this setup. Okay. So this is the kind of the setup we'll be taking for our lecture. Of course, there is another limit. Remember that in the second hydrodynamic limit, actually, we are going to take alpha to go to infinity. So in kinetic limit, alpha equals fixed. And then in the hydrodynamic limit, we'll set alpha go to infinity. Okay, alpha, this fixed constant will let it move and let it go to infinity. Okay, so this is the first thing that we take this n goes to infinity, epsilon goes to 0, and essentially under this scaling relation. Second, about the kind of the interacting system of particles. So in our paper, in our result, we're taking the simplest case of interaction, which is a direct collision. So the so-called hard sphere collision system, which basically says that two particles, they interact kind of only when they directly touch each other. So the picture is like this. Okay, so and then they go away in two different velocities. So basically the thing here is that like if the particles have diameter epsilon, then there is a formula. So the elastic formula that we have if the input velocity is let's say v prime, v1 prime, and this output velocity is v and v1, then the output velocity v equals basically v prime plus v1 prime minus v prime dot omega, and v1 equals v1 prime minus omega, where omega is the kind of this is omega is the direction of the vector that connects the center of the particles. So basically, you think that the velocity component in the parallel condition in the parallel direction omega is kind of just switched, like in one dimension. If the two particles they touch each other, okay, so exactly they touch each other, then the velocity exactly exchange in the completely elastic collisions. And then in the high dimensions, kind of the parallel direction of velocity is exchanged, while the kind of the orthogonal direction of velocity is kept the same. Okay, so this is a very simple kind of elastic collision system. And of course, like if the particles do not, if a particle do collide, we have this formula. If particles do not collide, then we simply have they just move linearly according to Newton's law. Okay, So this is the kind of the description of the system. So we have this parameter and epsilon fixed. We have this system. The rules of this evolution is fixed. Okay, and remember we are interested in this one particle density. Okay, we're interested in the evolution of these one particle densities and of course multi-particle densities. Okay, so historically there was these first ideas, by physicists that in order to derive this evolution of this density, they're making one key kind of assumption, which is called the propagational chaos assumption. So let me call it propagation of chaos. Or let's just actually the assumption is just referred to the chaotic molecular chaos assumption, which is basically saying that the states of different particles are independent. Okay, so this assumption, of course, is not true mathematically. And in what sense are we assuming this? In what sense can we say this is a highly non-trivial question? But let's say, if we kind of assume this, but this statement, this assumption is not very unintuitive. It is intuitive that different particles, we have so many particles that it's natural to assume that they don't see each other. They are not affected by each other somehow. Okay, so let's start with a very heuristic kind of formal derivation of the Boltzmann equation, so that we can see at least what the Boltzmann equation looks like if we assume this independent assumption. So we'll get back to this. Actually, the main component of our proof is exactly concerning like how this assumption is true and how it's understood to be true, or how it is understood to be kind of not quite true with corrections. But okay, so for now, let's assume we have this. Then okay, so what do we do? Okay, so say formal derivation. Okay, so because we want to analyze the evolution of the one-point density, so let's say we take the dt of f txv. So this is one-point density. Then literally, what does that mean? This means the kind of the rate of change of the densities at the position x and velocity v. Okay, so this means that at its position x and velocity v, of course, when you go past time t, there has been particles that originally at x and v, they move away. All their particles that are originally not at x and v, they move to the point x and v. Okay, so the first term on the right hand side is this transport term. Okay, so this just means that if there is no collisions, then the particles are moving straight lines, linear in time. Okay, and then of course the corresponding rate of change of the density is exactly given by this transport term. Okay, so if every particle just move linearly, you have this transport term. Okay. On the other hand, you are having this QFF, which is this collision integral in the Boltzmann equation, which come from the collisions. And how does this look like? Okay, this look like following: Q of FF, let's say TXV equals integral. Let's call it r to the d. Okay, so there is an integral of s to the sphere d minus 1, and we have this v1 dot omega plus, and then we have this f v prime. Sorry, let's say tx v prime f tx v1 prime minus f tx v f tx v1 d omega dv1. So let's understand what this term means. This term means that okay, so there is a positive term on the right side called the gain term, and there is a negative term called the loss term. Okay, so the gain term the positive term means the probability density of two particles at velocity v1, sorry, v prime and v1 prime collide to get particle of velocity v. Okay, remember we have this picture. The two things, how do we get the new particles at velocity v? It's possible that two other particles of two different velocities collide and they exactly get you a particle of velocity v. Okay. On the other hand, it is also possible that you have a particle originally of velocity v, it collides with something else, and then it changes its velocity, changes to something else, and this counts as a negative term on the right hand side. Okay, so now this term, this gain term, of course, the loss term is similar. This gain term has this form, but this gain term really means a probability of two particles. The probability that the first particle at velocity v prime, the second particle at velocity v1 prime. So you can think of it as a probability of the first particle at v prime, okay, second particle at v1 prime. Okay, and then if you assume this chaos assumption that these different particles are independent, then we can formally think of it as a probability of the first particle at v prime times the probability, because we're assuming independence, second particle at v1 prime, and then you see this will be given by the probability density, which is given by this f tx v prime times f tx v1 prime. Okay, so of course this is a completely formal derivation. There is no mathematical ground of it. You cannot just assume they're independent and they're actually not independent in reality. But this is something that is very intuitive, that suggests that we're having this particular form. So let's copy this here. So we get this Boltzmann equation, at least on the formal level. Okay, so this is a form of Boltzmann equation. Okay, so the kind of the rest of this lecture series is to actually rigorously justify the passage from the particle system to this equation. Okay. So before we move on, so there is one final thing we need to remark, that is the initial data. Remember that we are talking about these densities. This density, of course, we have this evolution of the system, but the density also has an evolution corresponding to this system, and we need to set initial data for this density. And since we are kind of expecting this independence, then the most natural thing is to say that we have this independence for our initial data. Okay, so this way we set the initial kind of density to be the S-point density Fs0 Z1 Ds. Since it's independent, we're expecting to have this joint density being a factorized thing, F0 Zj. Okay, so of course it's a symmetric product in the sense that the particles are indistinguishable, and of course one particle density F0 Z. So this exact initial data of the Boltzmann equation. Okay, so now we are kind of we have a completely kind of a formal mathematical statement. We start with this system with n particles and size epsilon, and there is this Boltzmann grad scaling. Okay, and then we have this this rule of interactions by this elastic collision that gives a precise definition of time evolution of the system. And then we have the initial densities given by these independent, these factorized structures. And then we want to evolve our density in time. And our question is in what sense can we say the density is given, in the limit is given by this Boltzmann equation. So this is our question. Can we show basically F1 Tz converges to a solution to Boltzmann? And of course, in what sense? Converges in what sense? And Fs Ds converges in what sense to the product in J of F1, the one-point density of T Tj. Okay. So this is the brief discussion of the setup of the whole problem. So before saying our main theorem, so let's review kind of the previous results. So there is a few kind of fundamental progress made in the 19th, so in the 20th century. So the first thing I would call it is this so previous results with work of Lanford, 1975, and of course King, 1975, where the result is that the kind of the derivation for small time. Okay, so there is a reason why these results are restricted to small time, which we may have a little bit time to discuss in the end. But this was a kind of the first milestone in this direction that completes the derivation, for sufficiently short time. And then there was work of Ilna Poverenti, I think 1986, where they kind of prove this derivation essentially for small data, or kind of the small, kind of, let's say, low density. So the alpha kind of, you can view it as a kind of small data problem, which again is it's a kind of in the perturbative setting. The work of Gallagher, St. Raymond, Pexia, 2014, they kind of completed this proof of Lanford, which actually there are some statements which are not kind of completely rigorous, and these paper kind of fill this gap, and they also obtain some kind of refinements and more precise descriptions of the limit. And after that, there has been this a series work of Bodino, Gallagher, St. Raymond, Simonella, where they look at various models, kind of linear models with a tagged particle, or kind of the perturbation of equilibrium, or kind of the perturbation to the Boltzmann equation, and they're kind of subsequent results, but again in the perturbative regime. Let me mention that these perturbative regime results, there has been a lot, like as of now, These are very good. These are important results. But in terms of the original question of going from the particle system to the fluid equations, these kind of perturbed results is completely not satisfactory because remember in the second limit, in the hydrodynamic limit, if you want your Boltzmann equation to connect to the hydrodynamic limit, you really do need this alpha to go to infinity. So this collision rate to go to infinity, and you cannot just stay at the case when alpha is sufficiently small. All the time is very small. There is a rescaling between time and alpha that if you let alpha go to infinity corresponds to the time go to infinity. So in any case, there is no way you can connect to the second limit if you are restricting to the perturbed regime, and that is the kind of the main starting point, the main motivation of our work. Our work is to exactly to provide a result, a positive result, where these alpha is allowed to be arbitrarily large, and of course, equivalently, the time of existence, time of validity is allowed to be arbitrarily large. Okay, so this is our. So let's first state our theorem, and then in the rest of this lecture, I'll talk a little bit about some basic ideas in the proof. So this is that's the convergence namely this F1 goes to the, let's say, n goes to infinity solution Boltzmann. It turns out this is the convergence is in the L1 norm in X and V. So let's see. So let's call it this way. So okay, and then the Fs the product in J F1 Zj. So that's Fs is true for arbitrarily large but fixed alpha, and for arbitrarily long time, again fixed, as long as the solution to Boltzmann exists. Okay, so this is our main theorem. So you see this is completely gets us out of the perturbed regime. That's the Boltzmann equation. It can it's arbitrary large data, and it may exist for arbitrary long time, and it may have completely different behavior at initial data. You have qualitative different behavior, and the theorem, our main theorem, tells us that all these kind of behavior is indeed exactly captured by the behavior of the microscopic colliding particle system. Okay, so let me make one remark. So there are few remarks, but maybe let me make two remarks. So our theorem is stated for the Euclidean space case. Also X in Rd, and there is also a parodic case where X belongs to torus, and we're doing the subsequent work in progress that deals the case of a torus. We believe it only requires kind of minor changes in the proof. And second point is that remember we're saying these values can be arbitrarily large. So in fact, They are allowed to go to infinity even, but there is a particular rate, when n goes to infinity. So the value of alpha and the time can be chosen to go to infinity as L goes to infinity, but they have to diverge slowly. They can diverge only like, so there's no L, so this should be n goes to infinity. Diverge like a log n. So it's a double log kind of thing. So our theorem, you can allow this size of alpha to be a double log and the time of existence to be again to be a double log. Okay, so this is our main result, and and for the rest of this lecture, maybe we'll have like 5 to 10 minutes. So I'll describe a little bit kind of the important ideas, like how to maybe first kind of intuitions, like the starting point, the motivations, and then we'll get more details in the next 2 lectures. Okay, so let's start from the beginning. So remember, in this formal derivation, like the key point is to assume that we have this independence, okay? Is to assume that, why this equals a product, why this equals a product of this and this. Okay, so let's say first, initial at time 0, we know that by assumption, the states of these particles are indeed independent, and we do indeed have this factorization at time 0. But of course, at positive times, at later times, these will no longer be independent, because you're having collisions, and if you have once you have 2 particles collide, then their kind of velocities will no longer be independent because they are kind of linked by this collision. Okay, but we still want to show that somehow this is true. So let's copy this here, and we see kind of in what sense heuristically can we say this to be true. Okay, so I don't think I can finish the ideal proof today, but we can continue next time. Idea 1. Okay, so we let's say we copy this here. Okay, so let's say we're considering the 2 particles that they collide, at velocity v1, v prime, v1 prime. So you see this is v prime, v1 prime. We know they are colliding at this time, this collision. Okay, so in what case can we say that the states of these 2 particles, this particle and the second particle, in what case can we say they are independent? They are independent means that remember that if once 2 particles they collide, then their states are not, their velocities are not independent. However, before they collide, or before they are connected by any collisions, their velocities are still independent. So the picture here is like this. So you have a, something, something that collide. Okay, so you have this guy. Okay, so 1, 2, 3, 4. Even if, let's say at this time, even if 1 collides with 2, 3 collides with 4, we still know that the velocity of 1 is indeed independent with the velocity of 3 because they haven't been connected by the collisions. Only after somehow later on, this is 1 and 2, okay, 3 and 4. Later on, let's say 1 collides with 3. And then after this time, that the velocity of 1 is no longer independent with the velocity of 3. Okay, because they are connected by collisions. Okay, so now let's go back to this picture. So these 2 particles of v prime, v1 prime, in what case can we say that their velocities are independent? That is precisely when these two particles, they are not connected by collision kind of in previous time. So let's say this is the collision at time t, then precisely when these two particles, they are not connected by collisions, then you can say that these two particles have independent velocities. Okay, so if you have independent velocities, then we can complete the derivation. So the only thing we need to show is basically to show that the case of a dependence, okay, the case of interdependence kind of have a vanished contribution in the limit. So independent implies the derivation. So dependence.
这太尴尬了。
Hello?
I guess no. You can continue. Yeah.
Okay,
Thank you.
okay. The dependence, has a vanishing contribution or not. Okay, so it turns out this is the main thing. One of the main points in the proof is to establish that the dependence indeed has vanishing contribution, and these correspond case of so-called recollision. Essentially, these two particles, they are connected somehow by collisions in previous times, and then they are colliding again at this time. Then this means a recollision, kind of, it's the collision that is more than necessary to connect these particles. So basically, we want to show that the case with where we have a recollision has vanishing contribution, and then that would imply, of course, module a lot of works that will imply in the end the validity of the Boltzmann equation. Okay, so I think I'll stop here. In the next time, I'll start with the short time result. I'll tell you, why exactly these results are restricted to a short time. And then starting from that point, I'll introduce our proof. How exactly do we kind of overcome this barrier of this short time, and how do we execute our strategy? Okay, then I'll stop here.